For this lesson, we'll be discussing the integrating factor technique often used in differential equations. For certain types of differential equations, the product rule can be used to solve it. So our product rule is f times g prime. So in order to find the derivative of a product of two functions, we take the derivative of the first function, multiply it by the second function, and add it to the first function multiplied by the second function's derivative. The specific form that the integrating factor technique can be used is for this. This is also a first order differential equation. So our integrating factor is mu of t is equal to e to the integral of g of t dt. To use the integrating factor technique, you must solve for the integrating factor, multiply both sides of the differential equation by it, and then use the product rule. So for our first example, we have the differential equation dy over dt is equal to negative 4y plus 9e to the minus t. In order to get to this form, we bring 4y over to the left side. Now our integrating factor is found by taking e to the integral of 4 dt, because 4 is g of t. This integral gives us e to the 4t. We do not get a plus c, even though this is an indefinite integral, because our plus c comes at the very end in our general solution. So now I chose to write this as y prime, because this is the first derivative, which is also dy over dt. So now we have the integrating factor. We can multiply both sides of the equation by it. So because these both have a base of e, we can add their exponents and get 9e to the 3t. Now for this, we distribute to each term. Now please notice that the derivative of e to the 4t is 4e to the 4t. So we have a function multiplied by the second function's derivative plus the derivative of the first function multiplied by the second function. So we have something very similar to this. So now we can use this property and take e to the 4t times y, group this in parentheses, and first derivative is equal to 9e to the 3t. Now we are able to integrate both sides, which is with dt. Now I have worked out the integral of 9e to the 3t. So to do this integral, we simply pull the 9 out, we have e to the 3t. We use u substitution to solve this. So u is equal to 3t, we eventually get our dt equal to 1/3 du. So now that we have this, we also know that the integral of e to the u du is just simply e to the u, so we will eventually get 3e to the 3t plus c. So now we have e to the 4t times y is equal to 3e to the 3t plus c. Now when we worked out this integral, see the integral of the derivative returns the original function inside. This is why the integrating factor technique is so helpful in differential equations. So now that we have this, we simply divide each side by e to the 4t. So our general solution is y of t is equal to 3e to the minus t, because the minus t was found by taking the difference of these two, so 3t minus 4t, and plus c e to the minus 4t. It is totally acceptable to leave this in the denominator. I just chose not to. Now also, I included that c is a real constant. I just wanted to let you know that c can change accordingly with the initial condition specified. Often in differential equations, we want to know how our function acts as it approaches infinity. Does it have an end? This is actually called the end behavior. So the end behavior is found by taking the limit as t approaches infinity of y of t. We find that these are both e to the negative exponentials. So what this implies is that this will eventually go to 0. So our end behavior, the limit as t approaches infinity of yt is equal to 0. End behavior is also important in signal analysis and understanding how signals behave over long periods of time. For our second example, we have a similar type of differential equation. It is already in the form we wanted. However, this one has an initial condition. So I chose to rewrite the dy over dt as y prime. So y prime plus 2y is equal to e to the t over 3. Our integrating factor is e to the integral of 2 dt, which is equal to e to the 2t. We'll multiply each side, and then we use the product rule, and we get e to the 2t times y prime is equal to e to the 7t over 3. Now we can integrate both sides by dt. So now the integral of this derivative just leaves us with the function inside. And this was found using the same u substitution technique for this 9e to the 3t integral. So now we have e to the 2t times y is equal to 3 over 7 e to the 7t over 3 plus c. We divide each side by e to the 2t, and we will get a general solution. Y of t is equal to 3 over 7 e to the t over 3 plus c e to the minus 2t, where c is a real constant. Now I choose to write my general solutions as y of t. It is perfectly acceptable to write it as y. The important concept when solving a differential equation is that we are solving for functions. In algebra or maybe some early math classes, you might have found a specific line or a specific number. We are dealing with systems in differential equations, systems of equations. So now that we have our general solution, we need to go back and use the initial conditions. Because our function is y of t, our t value is 0, and our y value is 1. So we plug these values in back for the general solution. So we get 1 is equal to 3 over 7 e to the 0, because t is 0, plus c e to the 0. Now, a number raised to the 0 power is 1. So this implies that 1 is equal to 3 over 7 plus c. So c is equal to 4 over 7. Thus, the solution to the IVP, now IVP means initial value problem. Because this differential equation has initial values, it is an initial value problem. And this is a very common abbreviation to use in differential equations. So our solution to this is y of t is equal to 3 over 7 e to the t over 3 plus c e to the minus 2t. Now, our end behavior is infinity, because when we evaluate the limit as t approaches infinity, this term will go to 0, but this term continues on for infinity. So if we thought of this as a signal, or in signal analysis just like behavior, it would just go on for infinity. So I hope this helped you in differential equations course, and thank you very much for watching.